In Chapter 9, we're going to be introducing confidence intervals, which will allow us to estimate the value of a population parameter. In 9.1, we're going to look at calculating or estimating the population proportion. Let's review some notation. P represents our population proportion. P hat is our sample proportion, where P hat is calculated x divided by n. Find the sample proportion if 12 out of 80 people prefer the color purple to all other colors. Our sample proportion is denoted P hat, and that's equal to x, which is 12, over our sample size, which was 80. We can simplify this. To 0.15. A point estimate is a single number that is our best guess for the parameter. The point estimate for our population mean is going to be our sample mean. The point estimate for population proportion will be our sample proportion. Sample statistics are used to estimate population parameters. So what we're getting into here is our inferential side of statistics. Based on data that we collect from a sample, what can we say about the population? In a study of 10,000 male newborn babies, 2 of them were diagnosed with hemophilia, a blood clotting disorder. Obtain a point estimate for the proportion of male newborn babies that were diagnosed with hemophilia. So we want the proportion of newborn babies that were diagnosed with hemophilia. Since this is going to be a sample, we're using P hat. 2 of our 10,000 babies were diagnosed with hemophilia. And if I convert this to a decimal, that is 0.0002. That is the proportion of male newborn babies diagnosed with hemophilia. Construct and interpret confidence interval for the population proportion. A confidence interval is an interval of numbers that is used to estimate the value of a parameter. It is determined by using data obtained from a sample and by using a specified level of confidence. So this diagram here shows the difference between a point estimate and a confidence interval. In this first graph, or the first image, it's showing what our point estimate is. In this case, the point estimate is 0.74. In the second, we're looking at our confidence interval. So again, the point estimate is our sample proportion, and the confidence interval is giving us a range of values that we think our population proportion would be based on our sample proportion. So looking at the example above, the point estimate was 0.74 and the confidence interval is 0.71 to 0.77. We can find this confidence interval by taking 0.74 plus or minus 0.03, which is the point estimate plus or minus the margin of error. So that 0.03 is our margin of error. The 0.74 is our point estimate. Our confidence interval is found by taking the point estimate and adding or subtracting our margin of error. We can write the confidence interval in 2 ways. The point estimate minus the margin of error is less than our parameter, is less than our point estimate plus the margin of error. Our point estimate minus the margin of error is equal to our lower bound. The point estimate plus the margin of error is our upper bound. Now we can also write this as an interval, the lower bound to the upper bound. And this is probably how we will most commonly write our confidence intervals. Now, an important note for proportions and means, we can determine the point estimate if we have our confidence interval. The point estimate is that midway between our lower bound and our upper bound. So if we take the average of those two, that will yield our point estimate. The lower bound plus the upper bound divided by 2. A 90% confidence interval for the population proportion of Americans who have donated blood in the last 2 years was found to be 0.168 is less than P is less than 0.194. Find the point estimate of the population proportion of Americans who have donated blood in the last 2 years. From that previous slide, we saw that we can find the point estimate by taking the average of our upper bound and our lower bound. So we're going to take 0.168 plus 0.194 and divide that by 2. Our point estimate is 0.181. Now we want to find the margin of error from the confidence interval. Well, we have our point estimate. Our confidence interval is equal to our point estimate plus or minus our margin of error. So 0.181 plus or minus whatever our margin of error is. Well, we know the two values for our confidence interval. We know that our lower bound is 0.168 and our upper bound is 0.194. So using either of these two, minus yielding the lower bound plus yielding the upper bound, we can solve for our margin of error. So using the formula for the upper bound, so our upper bound is equal to our point estimate plus our margin of error. We know that the upper bound was 0.194. We know our point estimate was 0.181 plus whatever the margin of error is. We can solve this for our margin of error by subtracting 0.181 from both sides. Our margin of error is 0.013. And you could test this by adding the margin of error to the point estimate and subtracting the margin of error from the point estimate and verifying that we get the same confidence interval. Once again, the confidence interval is used to estimate what the population parameter is. In this case, we're talking about proportions, but in general, we'll look at confidence intervals for means as well. We've got sample data, and we can get our sample statistic from that sample data. We're going to use that to construct a confidence interval for the population parameter. So once we calculate the confidence interval, either the interval has the true population parameter in it or it does not. Okay, it's one or the other. Now, we apply a degree of certainty or confidence before an estimate is made. So obviously, we want to be more confident. Typically, we will go with a 95% confidence level that the true population parameter falls within the interval. But there are some other common levels of confidence, 80%, 90%, 95, 98, 99% have all been used. The higher the confidence, or the higher the level of confidence, the wider your interval. That's because if I want to say I'm really, really confident, so let's say I want to be 99% confident, which is almost certain, I'm going to have to expand my interval, widen my interval to support that level of confidence, to ensure that I am actually that confident that the population parameter does lie in that interval and not outside of it. Your confidence level is equal to the probability that any possible sample will result in an interval that contains that parameter. Reread that statement. It's not the probability that the actual parameter lies in the interval. It's the probability that any given sample that we could possibly pick from the population will result in a confidence interval that does contain the parameter. So it's basically the proportion of confidence intervals that will contain that population parameter. Depending on the parameter, and this is the note here, depending on the parameter, we'll use different formulas for our confidence intervals, for finding sample size, and for what information is given. We're going to be looking at confidence intervals for proportion and means. Let's look at finding the confidence interval for proportion. The following formula gives the formula for finding that confidence interval. Remember that your confidence interval is your point estimate plus or minus the margin of error. We use p hat for our point estimate for proportion, so that means that this expression represents our margin of error. Now there are some requirements for using this formula. The first requirement is that n times p hat times q hat is greater than or equal to 10. That's our normality condition. And that our sample size is less than or equal to 0.05 times the population size. And that's just basically saying our sample size is no larger than 5% of the population. For the purpose of this course, we're going to assume that these are true, but in my stat lab, you might have to verify this. You can watch for the instructor tips to help you with these problems. Some of them are a little tricky, so we've added comments just to make sure that you guys are aware of how to solve them. Obviously, ask me questions anytime you have an issue. So if we're looking at that formula for the point estimate, we've got z alpha over 2 times the square root of p hat times q hat over n. P hat is our point estimate. Q hat is equal to 1 minus p hat. That's our complement rule. But what is that alpha? What are they referring to? So alpha is actually related to our confidence level. Our confidence level if you recall from the last slide, our common confidence interval, our most common is 95%, but we do 80, 90, 95, 98, 99. Our confidence level is equal to 1 minus alpha. So if I have a confidence level of 95, then alpha is going to be 1 minus that, or 0.05. In the case of our confidence interval, alpha always represents the total area in both tails of our standard normal distribution, and alpha over 2 represents the area in one tail. So what does that look like? If I draw my standard normal curve, and I look at the area in both tails, the area in both tails is equal to alpha, so the area in each tail is alpha over 2. Because of the symmetry, it divides evenly. And again, this is explaining that relationship between alpha and our level of confidence. If alpha is equal to 0.05, then the confidence level is equal to 1 minus 0.05, or 95%. There is 0.05 over 2, which is 0.025 area in each tail of the standard normal distribution. So far we're looking at a figure. We've got an alpha level of, or alpha of 0.05, which means that the area in each tail is 0.025. These two values of z, so this is going to be a negative z and this is going to be a positive z because of the symmetry, are called our critical values. We're going to abbreviate critical value with CV. Now we're going to draw a diagram for alpha equals 0.1. So again, we've got our standard normal curve. Alpha is equal to the area in both tails. So the total area in both of these shaded regions is 0.1. So that means that the area in each of our tails is 0.1 divided by 2, or 0.05. And then we could go back using that inverse norm function that we learned in chapter 7 to find the critical values for those areas. Another note on our critical value, when we're using critical values in our formula for our confidence interval, you're only going to use the positive critical value. As we mentioned before, that symbol Z alpha over 2 is representing our critical value for our distribution. And what that's representing is the number of standard deviations that we want to be from the mean and still result in an interval that contains the population proportion based on our level of confidence. Using the formula for the confidence interval for population proportion, determine the following. So there's our formula. Which piece of this formula is our point estimate? So our point estimate is going to be p hat. And which piece is the margin of error? That's what we're adding or subtracting from our point estimate. That is Z alpha over 2 times the square root of p hat times q hat over our sample size n. To find the values of Z alpha over 2, to find our critical values, we can use table 7 or we can use inverse norm. We learned inverse norm back in chapter 7. So I'm going to illustrate this for a 90% confidence level, and then I'm going to give you those values for 95, 98, and 99% confidence intervals. So for a 90% confidence interval, or confidence level, if our confidence level is 90%, that implies that alpha is equal to 0.10. Again, converting that percentage to a decimal, the two need to add up to 1. Alpha represents the area in both tails, the total area in both tails. So if I'm looking at my figure, the entire shaded region equals 0.10. Because this is symmetric, that means the area in each tail is alpha divided by 2, or 0.05. Now, using our inverse norm on our calculator, remember to access that, you'll do second vars, and then scroll down to inverse norm, and then you're typing in the area to the left. So I'm going to use this side of my graph because I have the area to the left is 0.05. So when I look at that, I do 0.05 for my area, and it gives me a z-score of negative 1.645. Because of the symmetry, that means this critical value is 1.645. As I mentioned before, when we're plugging critical values into our formulas, we're only going to use the positive values. So Z alpha over 2 for 90% confidence level is 1.645. For 95%, it's 1.96. For 98, 2.326. And for 99, 2.576. 2.576, sorry. Now I want you to notice that we rounded differently in each of those, and in fact we didn't. We're going to round to 3 decimal places for critical values. For that 95%, it's actually 1.960, but when we plug that in, the 0 is not going to affect the formula, so we don't typically write it. When interpreting a confidence interval, we're just going to fill in the blanks for the following sentence. So we'll replace confidence level, parameter, scenario, lower bound, and upper bound with the context from our problem. Let's go through an example of finding a confidence interval and interpreting it. A sample of 500 nursing applications included 12% from men. Find the 90% confidence interval of the true population proportion of men who applied for the nursing program. First, I'm identifying that they want us to find the confidence interval for the true population proportion. Well, we have that formula. The formula for confidence interval for proportion is p hat plus or minus z alpha over 2, which is our critical value, times the square root of p hat times q hat over n. Now, I like to begin by writing the formula I'm going to use because that helps me identify what information I need to pull from the problem and what variables I need values for. So I need p hat. They tell us that 12% of men, 12% of the applications were for men, so that's our p hat, 0.12. I also need q hat. Well, p hat and q hat are related because they are complements of one another. So q hat is equal to 1 minus p hat, or 0.88. I need the value of n. N is 500. And I need z alpha over 2. Now, to find that, I need to identify what the value of alpha is. Alpha is going to be 1 minus my confidence level. So I have a 90% confidence level, which means alpha is 0.10. We're going to use this to find our critical value. Remember, alpha represents the total area in both tails. So if the total area is 0.10, that means that the area in each tail is 0.05. Using my inverse norm, I can find that critical value. If I use this left-hand side, I have the area to the left is Using, again, inverse norm, the area to the left is 0.05, and I find my critical value is negative 1.645. And this critical value is then positive 1.645 because of the symmetry. Now, when we're using our critical values in our formulas, we're only going to use that positive one, so I now know that z alpha over 2 is 1.645. Now that I have all the values for my formula, plug and chug. P hat plus or minus 1.645 times the square root of 0.12 times 0.88 divided by 500. I would pause the video here and try entering this expression. And now you're going to enter 2. You're going to do 0.12 plus the rest, and you're going to do 0.12 minus that value, that 1.645 times the square root. So you're going to do 2 calculations. Go ahead and pause this and type those in, and then come back and compare your answers. The lower bound for the confidence interval is 0.096, and the upper bound is 0.144. If you have any issues finding these lower bounds and upper bounds, so typing it into our calculator, bring those questions with you to class and we can go over it in person. Lastly, we need to interpret it, and we're going to use that sentence up here, just filling in the blanks. So we are 90% confident that the true population proportion of men applying for the nursing program is between 0.096 and 0.144. Again, the only things that we pulled from the actual problem are level of confidence, The parameter that we're using, in this case, we're talking about proportion. A description of the scenario, the lower bound and the upper bound of our confidence level. We'll use the exact same setup every single time when we're interpreting. Sleep apnea is a disorder in which you have one or more pauses in breathing or swallowing while you sleep. In a study of 320 individuals who suffer from sleep apnea, it was found that 192 also had gum disease. Find the 95% confidence interval to estimate the proportion of individuals who suffer from sleep apnea who have gum disease. The problem is asking us to find the 95% confidence interval to estimate the proportion. That tells me the formula that I'm going to use. Again, the formula for confidence interval for proportion, p hat plus or minus z alpha over 2 times the square root of p hat times q hat over n. Knowing what formula we're using, again, helps us in identifying the values of those individual variables and what we need to pull out from the problem. (192) of our 320 individuals also had gum disease. So that's how we're going to find our p hat. It's going to be that ratio of 192 over 320, which is 0.6. Q hat is 1 minus 0.6, or 0.4. And our study had 320 individuals. Our confidence level is 95%, which tells me that alpha is 0.05. And we're going to use this to find our critical value z alpha over 2. I always like to calculate my critical value by hand just because training myself to do this process is wonderful when my level of confidence isn't one that's necessarily predetermined. We do have those common levels of confidence, but if it's a 92% confidence level, we don't know those critical values by heart. So knowing how to do it is important. Alpha represents the total area in both tails. So if the total area in both tails is 0.05, the area in each tail is 0.05 divided by 2, or 0.025. Using inverse norm and the area to the left being 0.025, the critical value down here is negative 1.96, and the positive is positive 1.96, and we will only use that positive value. So 1.96 is our critical value. The more confidence intervals that you set up, the more likely it is that you'll remember these common critical values. Now we substitute all of the values for our unknowns. 0.6 plus or minus 1.96 times the square root of 0.6 times 0.4 divided by 320. Again, this is going to be two separate calculations, one where you're using addition, one where you're using subtraction. Go ahead and pause the video, type these in, come back and check your answers with mine. The lower bound is 0.546. Our upper bound, 0.654. Next, we will interpret this. We are 95% confident that the true population proportion of individuals who suffer from sleep apnea and have gum disease is between 0.546 and 0.645. Now, I know these seem wordy, but it is important that we follow that same structure. Again, the only things that we got from the problem, 95%. We're writing a confidence interval for proportion. The next, we're describing this scenario of individuals who have sleep apnea and have gum disease. I pulled that directly from the problem. Individuals who suffer from sleep apnea and who have gum disease. I didn't have to come up with it on my own. I just copied from the problem, and that's A-okay. And then we plug in our values for our lower bound and our upper bound. The last thing we're going to look at is determining the necessary sample size for estimating a population parameter within a specific margin of error. From our formula for population proportion, or the confidence interval for population proportion, we know that E, which is our margin of error, is equal to our critical value times the square root of P hat times Q hat over, this should be N. Oops. Now, this formula can be solved to isolate N, and the formula will then look like N equals P hat times Q hat multiplied by the critical value over our margin of error squared. Now, it's important to note that we will always round up to the next whole number when we're determining sample size. We're trying to find the sample size necessary, so the minimum sample size necessary for a specific margin of error. Also, in some situations, we're not given our population, or our sample proportion. So if we're not given our sample proportion, we're going to assume that both P hat and Q hat are equally likely, and their probabilities or their values are 0.5. A researcher wishes to estimate with 95% confidence the proportion of people who own a home computer. A previous study shows that 40% of those individuals, those interviewed, had a computer at home. The researcher wishes to be accurate within 2% of the true proportion. Find the minimum sample size necessary. Again, we want to identify what we're trying to find in the problem, and then we can go back and pull the necessary information that we need from the context of the problem. They're asking us to find the minimum sample size. So that indicates what formula I'm going to use. I'm going to use the formula N equals P hat times Q hat times our critical value divided by our margin of error squared. Now, I would like to add that we've also identified that we're talking about proportion in this problem. The formula for determining sample size will change if we're looking at mean, not proportion. So just another note to that. But now that I have my formula, I need to identify the values of my unknowns. So I need P hat, I'm going to need Q hat, I'm going to need my margin of error, my value for alpha, which will then allow me to find my critical value. All right, so let's look at some more details from our problem. We have a 95% level of confidence, which tells me that alpha is 0.05. A previous study shows that 40% of those interviews had a computer at home, so that's my P hat. My Q hat is going to be 1 minus that, or 0.60. And a researcher wishes to be accurate within 2%. That's my margin of error. But we need to make sure we convert that to a proportion, so that's going to be 0.02. Like we've seen in previous example, if we have a 95% level of confidence, or alpha equals 0.05, then our critical value is 1.96. And now that we have all the values of our unknowns, we can substitute them into our formula to determine sample size. N is equal to 0.40 times 0.60 times 1.96 divided by 0.02 squared. According to the order of operations, we have to do this part first. So divide 1.96 by 0.02 and then square that number. Once you have that value squared, then you can multiply it by the 0.40 and 0.60. When you plug this into your calculator, you should get 2,304.96. But as we mentioned before, you're always going to round up to the next whole number. So N is equal to 2,305. That is the minimum sample size needed. The same researcher wishes to estimate the proportion of executives who have a company car. She wants to be 90% confident and be accurate within 5% of the true proportion. Find the minimum sample size necessary. We want to find minimum sample size, and we're dealing with proportion. So our formula, N equals P hat times Q hat times Z alpha over 2 divided by our margin of error squared. Now looking through the problem, we can identify what our values of P hat are and Q hat, E, and our critical value. So P hat, if we look in our problem, we're not given P hat, so recall that we're going to use 0.5 for our estimate of P hat, which means Q hat is also 0.5. And basically what they're saying is that it's equally likely that an executive would have a company car or not. Since we don't know for sure, we want to be as conservative as possible. Our margin of error, we want to be within 5% of the true population proportion, so our margin of error is 0.05. Our level of confidence is 90%, so alpha is 0.10. We've seen that for a alpha level of 0.10, our critical value is 1.645. Now that we have all the values, we can substitute them into our formula. N is equal to 0.5 times 0.5 times 1.645 divided by 0.05 being squared. Go ahead and pause the video, type this in, and check your answer with mine. When you plug this in your calculator, you should get 270.6025. We're always going to round up, so N is equal to 271. For your homework, if your critical value can't be found in Table 7, which you'll review that in class, then we'll use inverse norm like we've been doing up to this point. And we've been a little lazy in the last two examples, not drawing the figure and actually solving for our critical value because they were common levels of confidence. But again, sometimes you won't have a common level of confidence. So let's look at an example that's not so common. Let's find our critical value for a 94% confidence interval. If our level of confidence is 94%, that means that alpha is equal to 0.06. So if I draw my figure, that means that the total area in both tails is 0.06, or the area in each tail is 0.06 divided by 2, which is 0.03. Again, using inverse norm on our calculator, we're going to work with that left-hand side because the area to the left is 0.03, and we'll find the negative critical value, and then we'll report the positive. So marking the area to the left is 0.03. The critical value is negative 1.881. Again, critical values we will always round to 3 decimal places. And then our positive is positive 1.881. And our Z alpha over 2, the critical value that we'll use for finding the confidence interval, is 1.881.